So for these radioactive dating practice problems, there's 4 pages of problems, so I'm hoping to do these maybe in 2 different videos. So we'll start it with the first one now. So a geologist determines the age of a rock to be 2.1 billion years. So anytime you're given the age of a rock, you know that you're going to have to divide by the half-life value. And if you read through the problem, it says the half-life value is 0.7 billion. So we're going to take the 2.1 billion and we're going to divide that by the 0.7 billion, and we're going to determine that we have 3 half-lives. So for the purpose of a public exam or a unit test, you'd probably get 1% for accurately determining the number of half-lives that have occurred. We can also see that this is a problem whereby you're going to be working with grams. So we're going to set up a parent-to-daughter ratio. This is going to be the number of grams of parent that was in the rock or the bone initially, and this is going to be the number of grams that was remaining in the rock. So let's see what we have. It says we have 15 grams of uranium remaining in the rock. That tells us that the 15 grams goes here. Whatever this number was right here, it would have got divided by 2, divided by 2, divided by 2 to give us 15 grams. So we just need to do the opposite, and instead of dividing by 2 3 times, we're simply going to multiply by 2 3 times. So when we do that, 2 times 15 is 30, 2 times 30 is 60, and 2 times 60 is 120. So that tells us that the final answer is that 120 grams of parent was actually in the rock in the beginning. Moving on to the second problem, it says radioactive atoms of potassium-40 will decay with a half-life of 1.31 billion. How many billion years will it take for 20,000 atoms to decay so that there's 2,500 atoms left? So if we were to have a parent-to-daughter ratio, they're basically saying that we have 20,000 atoms of parent, and now we only have 2,500 atoms. So what we're going to do is we're going to see how many times we need to divide by 2 so that 20,000 becomes 2,500. So 20,000 divided by 2 is 10,000. Divide that by 2 is 5,000. Divide that by 2 is 2,500. So we essentially had to divide by 2 3 times. That tells us that we have 3 half-lives. If we know that time for one half-life is 1.3 billion, all we need to do is to multiply it by 3. So if you were to take 1.31 billion and multiply that by 3, then the answer would be 3.93 billion years old. Moving on to the third problem, it says analysis reveals that a trilobite sample contains 12.5% parent and 87.5% daughter. So that tells me that we need to set up a parent-to-daughter ratio, and in this particular case we have 12.5 to 87.5. So in order to reduce a ratio, you divide both sides by the smallest number. So 12.5 divided by 12.5 is 1, and 87.5 divided by 12.5 is 7. So we have a ratio of 1 to 7, which means 1/8 of the parent is left, which means we have a half, a quarter, 1 over 8, which means that we actually have 3 half-lives that occurred. The question says how many half-lives have passed, so we've already got the final answer in this particular case. Moving on to the next problem, what is the half-life in millions of years of the element or the isotope represented in? So we'll have to go and see for a half. So the way I would read this particular problem is we start out with 100 right here, and that is amount of parent material remaining, and so that lines up on the x-axis with 0, which means no half-lives. So if we were to take 100 and divide it by 2, we'd have half of 100, which is 50. If we come over and touch the curve and come straight down, it would tell us that the half-life in this particular case is 100 million years. Moving on to the next problem, a bone was found to be 45,840 years. So what we're going to do, we're going to take the age of the bone, which is 45,840. Note it's in years. I don't have room to put in my units, otherwise I would. We're going to divide that by the time that it takes for one half-life, which is 5,730 years. So I'll just grab my calculator quickly, and we will go 45,840, and we're going to divide that by 5730, and we know that we have 8 half-lives. That's how many that actually occurred. And so this is a problem that involves grams. So this is going to be parent in the beginning, and this is going to be parent now. And it says if there was 520 grams initially in the bone, that tells me that this here is 520 grams. We got to divide by 2 8 times to see what this number is. So we have 520 divided by 2, that's 1. Divide by 2, 2, 3, 4, 5, 6, 7, 8. And that tells us that our final answer is 2.03 grams. That's the number of grams of parent that's actually remaining in the rock right now. If we go on to the next problem, problem 6, without even reading the question, to be honest, I quickly see right here that we have a ratio of 1 to 127. So that tells me that that is a fraction of 1 over 128. So 1 over 2, 1 over 4, 1 over 8, 1 over 16, 1 over 32, 1 over 64, 1 over 128. So that tells me that we have 7 half-lives that have occurred. Now, if we look through the problem, it says the half-life value for the isotope pair is 713 million. So we had 7 half-lives, so we're going to have to multiply 713 million by 7. So 713 multiplied by 7, that tells us that we have a rock that is 4.991 billion, or you could read it as 4,991 million years. On to the last problem for this particular video. It says a geologist discovered there are 20 grams of parent remaining in a rock. Okay, so we're going to set up our parent to daughter. This is parent now, this is parent remaining, and the parent remaining is 20 grams. So this is the type of problem where they're going to say how many grams of parent are remaining in the rock in the middle, okay, or sorry, in the beginning. So the age of the rock is definitely going to be known, and if you look, there it is, and the time that it takes for one half-life is going to be known. So we're going to take the age of the rock, which is 6.55 billion. So it's a rock that's much older than Earth, so maybe it's a meteor that came from space. And we're going to divide it by the half-life value, which is 1.31. So we'll take 6.55, we'll divide that by 1.31, and we will determine that 5 half-lives occurred. So whatever this number was that we're trying to figure out, it got divided by 2 5 times to give us 20. So we're going to do the opposite, and we're going to multiply by 2 5 times. So we're going to go 20 times 2, 40 times 2, 80 times 2, 160 times 2, and that's 320. Now, how many times did I do that? So 20 times 2 is 40, 80, 160, and 320, so I need to do it once more. And so the final answer would be 640 grams of parent was in the rock in the beginning. Alright, so I'll stop the video there and I'll pick up in a second.